Hello, my people. Good morning, good afternoon, good evening. This is Dacian. I'm happy to be here again. Welcome to Mathify Analytics. I hope you have been well. In today's video, we are going to continue what we started last time. In our previous video, we saw how to calculate the discrete probabilities. It was a theoretical view. We saw manually how to build discrete probabilities, how to calculate the mean and the variance for different discrete probability distributions. In this video, we are going to go soft. We are going to go soft. We are going to use R, and we are going to discuss how to calculate binomial probabilities using R. In this video, we will see how to calculate exact probabilities, cumulative probabilities, and of course quantiles, and we are going to see how to simulate binomial probabilities and binomial trials, and finally we see how we can construct histograms of calculated binomial probabilities. I hope you're going to enjoy today's video, and if you like the video, don't forget to click like and share the video. If you happen to be here on this channel for the first time, subscribe to our channel and make sure to turn on notification bell so that you'll get notified anytime we upload a new video. So enjoy. I hope you're going to enjoy today's presentation. So before jumping into calculating these probabilities, let us recall what the binomial distribution do. The binomial distribution models the number of success in a fixed number of trials, of course independent trials, with equal probability of success. So for a binomial distribution, we need two parameters. We need number of trials. Let me call it n. N is the number of trials. Let's say we have 5 trials, and the probability of success. Let me say that we have the probability of success to be equal to, let me say, 0.5. So to calculate exact probabilities, let me say that we want to calculate the probability that kx is equal to, let me say, x equal to x equal to 3. Probability that we have number of success to be equal to 3. This probability, we have to use the function dbinom. So dbinom, the function is dbinom, and this function takes two arguments. The first argument is the number of trials, and the number of, not the number of trials, the number of successful trials. In our case is 3, and the number of total trials, or the trials, are 5, and the probability of success. The probability of success in our case is 0.5. So let me use n and p. So n and p. Then n is not known because I've not told what is n. So n is 5, yes, and p is 0.5, and then this probability. So the probability will be equal to 0.3125. Exact probability. If we want to calculate the probability that the x is equal to 4, then it will be the binom. Then you enter 4 and n and p. Yes, and if you calculate this one, the probability will be equal to 0.15625. And what if you were asked to calculate the cumulative probability distribution? Let's say the probability that x is less than or equal to 3. So in this case, we'll use another function, not binom, but the p-binom. You use p-binom, and then it will also take the number of success. Number of success in our case is 3, and it will take the total number of trials and the probability of success. And if you compute this, it will be 0.8125. This is the probability of having x less than or equal to k. And if you want, you can use this argument called lower tail equal So in this case, because we have less than or equal, the lower tail is true. Then you enter T or you write true. Then if you do this, you get the same number. And if you have to compute the upper tail, then upper tail will be, for this case, probability x greater than or equal to 3. You can calculate it by using P binom, of course. It's P binom, and you enter your successes, and then the number of trials, the N and P, and then in this case you have to enter lower tail to be false, because you have to compute x greater than or equal to 3. So then in this case it will be 0.1875. And if you don't use this argument lower tail to calculate the same probability, you can take 1 minus the probability of having x less than or equal to 3. So then minus P binom, P binom 3 and N and P, like this. So you will get the same probability, 0.1875. You can use whatever method you want. Either you can use lower tail to be false, or you can take 1 minus the probability of the lower tail. All right. So the other important thing is to calculate the number of successful trials having the cumulative probability distribution equal to k. So here, the probability of having x less than or equal to k to be greater than or equal to k, how many successful number we have. In this case, to calculate the number of successful trials having a given cumulative probability distribution will be calculated using the function Q binom. So then Q binom. So let's say we are going to calculate the first quantile. I hope you know how to calculate it. Then the probability of having the first quantile, the first quartile is 0.25. Then you enter it, and then you enter the number of trials and the number of probability of success. Then in this case we will have how many? 2. Then you have 2 successful trials. Yeah, that's how it works. If you need 90% quartile or 75% quartile, in this case you can use, let me copy this and paste it here. Yeah, and you can use in this case the probability to be 0.75 if you want the 4th quantile. Yes, then if you click enter you will have 3. Yeah. So the other thing that we can do is to simulate the binomial outcomes. Let me say that I want to, from this binomial distribution that we have been working with, binomial distribution with n equal to 5 and p equal to 0.6, 0.6, we are using 0.5, sorry, 0.5. They say that I want to simulate 10 outcomes from this binomial distribution. Then I will have to use another function called the R binomial. R to mean random. So then R binom, and it will take the number of outcomes we want to simulate. Then we say I want to simulate 10. Then 10 n and p. And then if I compute n, I will get this 44104. Then these are 10. Of course, this means that I may have 4 successful, and 1 success, 0 success, and so on. So it depends on how many outcomes I want to simulate. Yeah, so that's how it works. Yes. So before going on building a histogram, let me first talk about how we can calculate the variance and the standard deviation. From the last video, we saw that how when we want to calculate the mean, we take n times p. N times p, the probability of success times the total number of trials. So for our case, the variance will be equal to n times p. N times p. P times p. So the variance will be equal to 2 power, not variance, the mean. The mean is n times p. So the mean for our case is 2.5. And the variance for our binomial distribution, if we use the formula that we saw in our previous video, it is n times p times first put times 1 minus p times 1 minus p, and the variance is 1.2025. But then there is something that I want to tell you. From these simulated values, let me call these simulated values, these simulated outcomes, let me call them x equal these simulated values. Let me know these values. And if you want to calculate the mean from those simulated values, you don't need to use the n times p. You can just type mean of x, then mean x and enter. You see the mean is 2.3 and the true mean is 2.5. And you see 2.3 and 2.5, it's closer but they're not exact. But what if we increase the number of outcomes that we generate? Let me say that we generate 1,000 outcomes. X equal I enter x. I generate 1,000 outcomes from our binomial distribution. If I compute the mean now, the mean is 2.472. You see, it's closer to 2.5. So you see, when you are sampling, please don't use a small number when you are sampling. So when n is small, so this is not a good sampling. When you are sampling, take a big value of sample size. The sample size should be big so that you will be closer to the true, so that the mean you want to calculate will be closer to the true mean of your distribution. And this is the same for the variance. If you want to compute the variance, in this case you have to use the function var, then the variance var x, then the variance is 1.201 and the true variance is it was 1.225. so you see it's closer. Yeah, so you see, that's good. So finally, the other thing that you can do is to make a histogram of your distribution, your sampled this outcomes from a binomial distribution. And the function that do this is the hist function. And the hist function, what it will take x. And you may also need to use the breaks. And the breaks will be breaks equal, let's say that we have to take values, because we have 5 outcomes, so it may be 0, 1, 2, 3 or 4. So then take the sequence. Then the sequence from let me say minus 0.5, yes, and up to 5.5. I take minus 0.5 because I want the 0 to be in the center of our bar that we're going to sketch, and 5 also will be in the middle of the bar. So then by 1 by equal to 1 by equal to 1, the steps in between bars is equal to 1. Here you can also give a title to your histogram, and the title is under the argument main, and main equal let me say histogram of simulated binomial outcomes. Yes, and you can also specify what the x-axis will be called. Then this will be x-lab. X-lab will be equal to successful outcomes. Let me success. This is success. Number of success. This is the number of success. And you can also specify what will be on the y-axis. Then this is y-lab. And the y-lab, let me call it, if you want it to be probabilities or frequencies, whatever you want. Let me first start with frequencies. Let me say that we want the frequencies. Frequencies, yes. Yeah, and then the other argument that we need is the probabilities. Probability equal because we need frequencies here, then the probability equal false, like this. And if we call this, then we will have an expected equal breaks. Let me see what's the problem here that we have. This breaks, not break. Yes, breaks. Then this is hist, not his. So please make sure that you type everything well. Yes, then you get your histogram here. Yes. So you can see that our histogram has a gray color. If you want, you can change the color of your histogram, and to change it you use the argument core. And then let me say I give a blue color, then this one, yes. And if you want, you can change the borders of your balls, whatever you want. And to change the borders, as you can use the argument border. How do we do it? This is border, yes, borders. And let me say the borders are white. Instead of having these borders, you see that they are black. So let me say that I want white borders. Then I will put white there. Then I hit. So you see that you get this white borders, whatever. So if I want to have, you see that here on the y-axis, here, let me make this one bigger, a little bit bigger. So I minimize it instead of making it bigger. Yes, if I make it bigger like this, so you see that here on the y-axis I have frequencies. So if you want to have probabilities, you have to change this probability argument into true. Instead of having false, put it through there. If we put through there and click enter, so you see we have now the probabilities on y-axis. So you see, so I hope now you understand how you can use R to calculate the probabilities of binomial distribution. And in our next video, you remember that in our previous video we discussed about different discrete probabilities. It was not only the binomial distribution, there were also Poisson distributions and the geometric distribution. In our next video, I will talk about how we can calculate the Poisson probabilities and geometric probabilities. But let me see if I will use R or Python, whatever. Or if I don't do about that one, then I will show you how to do the same as we have done here in R using Python. Go in the comment section. Let me know if you want to see also how we can do this in Python, or if you want to continue with R and move to another distribution. Yes, and I will do what you want me to do. So if you don't comment, I will do it the way I want it. But if you comment, go and comment and let me know what you need me to do. So yes, so that's it for today. I hope you have learned a lot from this video, and if you happen to like the video, don't forget to click like the video and share the video to your friends. First, thank you for watching and see you for the next time. Bye.